All right, so this would be the first problem that we try our our conjugate beam method on. So let's get started with that. I'm going to first draw the shear and moment diagram for this guy. To do that, I'm going to need to find the shear and the moment. I'm going to assume positive shear and positive moment. I'm going to slide over here to the side and I'm going to find those values. So first I'm going to sum moments about A. Make sure things are in equilibrium. When I do that, my reaction moment here at A with my sign convention is negative. I forgot to actually subscript those A. And then also the moment due to the 5 kip applied force at a distance of 15 feet. So it looks like my moment at A is negative 75 kip feet. And then I'm going to sum forces in the y direction. I'll assume up is positive. Make sure everything's in equilibrium. So looking at my free body diagram, I've got the shear force acting up, 5 kips acting down. So it looks like the shear at A is 5 kips. That's not so bad. So I'll draw a little section here, and we'll construct the shear and moment diagram. There's my positive x, positive value for shear. I'll let all my units be in kips. So what's our starting shear? Shear at A is 5. Also, I'll add this to my template. That's going to be a point I'm curious about. So I'm going to start at 5. There's no load over the first 15 feet, so there's no change in the shear, so that's going to stay constant. Then I'm going to, as I go from the left side to the right side, this 5 kips will bring it down to 0, and I'll have no more shear. So my shear diagram is that. Constant shear over the first 15 feet, no shear over the second 15 feet. Then I will look at my positive moment, positive x-axis, and I'm going to do this in kip feet for my units. Looking at our moment, it starts off at negative 75. The change in moment over the first 15 feet is the area in the shear diagram, which is positive. And it's also 75, which brings us to 0. And of course, the slope of the moment diagram is the shear, and the shear is constant and positive. So I get a nice triangular shape for my moment diagram. The change in moment from 15 to 30 feet is 0 because there is no shear. So there's my moment diagram. So let's see how best I can. So I'll put my conjugate beam here. Let's see if I can squeeze this in. So our conjugate beam geometry. The fixed connection of the real beam becomes a free end, and the free end becomes a fixed end. So we get a structure that looks like this. And now I'm going to take this moment diagram, I'm going to go over here and apply it. So what I like to do is just take the moment diagram and pick it up and just drop it right on there. See that? It's almost like you could take that and just slide it right over and drop it right on there. So this will still be 15 feet. This will still be 15 feet. Now this moment is negative. Which direction is negative load, up or down? Down. That means I now have a load applied to my conjugate beam that has a value of 15 kip feet, that's my moment, divided by EI. So there's my conjugate beam. Now you have to ask yourself, what do you want to know? Well, for in this problem, I want to know the slope and displacement at B. B is here in the real beam. This is B in the conjugate beam, which is the fixed connection. So if I come over here and write that I know here's my positive shear at B and here's my positive bending moment at B, right? If I can find the shear here at B, what is that in the real beam? The slope. If I can find the moment here at B, what is that in the real beam? Displacement. That's what I want to know. So I just need to find these reactions and I'm done. So to help things out, I'm going to come back and I'm going to get a concentrated equivalent force. I'll just call it F1. We'll figure that out in a second. And then I'll have to figure out this distance from B to F1. I'll call it D1. So let's do that real first. So what is F1? It's just the area under this triangular section. So F1 will be 1/2 for a triangle times the base, which is 15 feet, times the height, which is 75 kip feet, divided by EI. I don't know what that is off the top of my head. You guys are going to have to help me out. So it's going to be 15 times 75 divided by 2. So while you're figuring that out, I'll go ahead and figure out what D1 is. Well, D1 is going to start here. I'm going to go 15 feet. And then from this point, how far is it more to the centroid? Well, it's 2/3 of 15, which is 10, right? 10 plus 15, this should be 25 feet. Anybody get a value for F1? Nobody?
562.5.
I don't know. Does that sound pretty good?
That's probably right.
So 562.5, and that's going to be kip feet squared over EI. So let's just find those reactions. So I'll start by summing the moments at B. Make sure it's in equilibrium. I'll use right-hand rule. So the moment at B, is that positive or negative with my sign convention? Positive. This force, equivalent force F1, what kind of moment is it creating about B? Positive or negative? Positive. So it'll be F1, which is 562.5 kip feet squared, divided by EI, times distance D1, which is 25 feet. So that means I can solve for the moment. What is the moment at B? Looks like it's going to be negative. Just multiply that by 25. What do you get?
1,462.5.
4,400.
14,062.5.
14,062?
Yeah, 062.5. I'm sorry.
That's okay. And that's going to be kip feet cubed over EI. It came out negative. Would you expect the displacement at B to be negative, which is down? Yeah, seems reasonable. In fact, we can now, because we have values for E and I, we can actually compute. So the moment at B really maps into the displacement at B, which would be negative 14,062.5, and that's kip feet cubed. And I'm going to do some calculations here. So I'm going to divide by E. E is 30,000 kips per inch squared. I is 800 inches to the fourth. And then I'm going to say that there is 1,728 inches cubed in a foot cubed. If you look at that carefully, you can see my feet cubed cancel, my kips cancel. I have inches to the fifth over inches to the fourth, which is inches. And what does that come out to be? 1.01 minus 1.01. That's one. So basically 1 inch. How do I find my slope? I just sum forces, right? I may have to squeeze this in over here. So if I sum forces in the y direction, what do I have? Well, I have my shear acting down, and then I have my value for F1 acting down. Right? So that means the shear at B is equal to minus F1. F1 is 562.5 kip feet squared divided by EI. So it says my slope is negative. Does it make sense that would have negative slope at that end? Well, I think it's going to deflect something like that. Displacement's down, and if you look at that slope, it's negative. So that seems to match. So just to give you the numerical value, the slope at B is going to map into the shear at B is going to be the slope at B. Yeah, you guys can see that. So I've got minus 562.5, and that's kip feet squared. I just wanted to show you this one because the unit conversion is a little bit different. We're still going to divide by E, which is 30,000 kips per inch squared. I, which is 800 inches to the fourth. But now I just need to convert feet cubed. So that would be 12 inches in a foot. Cubed is 144 cubic square inches in a square foot. Now if you look at those units, feet squared, kip, inches to the fourth, it has no dimension. So what's that number? It's going to be probably something very tiny. So the units of this are going to be in radians. And you might remember that there's 2 pi radians in 360 degrees. So that's how you can convert that. Pretty small angle. Okay. Sorry for running a little late.